The previous video emphasized the advantages of using machine learning methods to analyze choice data. In this video, we investigate several aspects that are important and for which discrete choice analysis is superior to machine learning. So I started to mention that machine learning is very useful. It can even be superior to discrete choice for model specification, model development, model selection. I have also presented some pitfalls that are relatively easy to fix if you are aware about them. But there are some aspects where discrete choice is superior in the sense that there are important aspects that discrete choice can do that is not necessarily possible with machine learning. And this is what I would like to review now. I have selected 4 of them: extrapolation, policy analysis, sampling, and interpretability. Let's reintroduce the notation. So we will use the same notations as we have done in this course. So the explanatory variables will be called x, and the choice will be called I. So we have a data generating process which is provided by nature or by the behavior of individual that I denote by small p I of x. This is the true data generating process. What we do in discrete choice is that we postulate a theory that characterizes the causal relationship between the explanatory variables x and the choice. So this is the choice model. We can write it as the probability of I given x, and then we have a set of unknown parameters theta that we estimate from data. This is based on theory. Machine learning is not based on theory. It's data-driven. So it investigates the distribution of the data. So somehow what machine learning methods provide is a model that also predicts I as a function of x. So I will denote this by q. But instead of using the theory, they use data. So somehow they approximate this model by the observed joint distribution of I and x divided by the distribution of x. So this is a statistical way or a probabilistic way to interpret the machine learning method. So let's now go through the important aspects that I would like to discuss in the context of discrete choice and machine learning. The first is extrapolation. What is extrapolation? Is when you want to predict the class or the choice for values of x which are outside the training data. Machine learning, as we have seen, focus a lot on goodness of fit using this training validation set. So it's usually very good for interpolation, but it may be poor in extrapolation. And I would like to illustrate this on a simple example. The setup of this example is regression. This is simpler for the sake of illustration. If you want a detailed discrete choice example, which is similar, you can see the video called Survival of the Fittest or Not, which is available on YouTube, where I basically provide an example of overfitting. So let's take a regression model where we want to predict the number of trips performed in a city as a function of the cost of public transportation. And I will assume that the true data generation process is given by something which is t, which is the number of trips, which is a constant, plus a term that decreases with the cost of public transportation. Now, in order to illustrate my point, I will, on the one hand, propose a theory. Okay, my theoretical model is based on the assumption that the number of trips will decrease with the cost of public transportation. But I don't know the true function, so I will postulate a function, I will make a mistake, my model will not be the true model. For example, I will assume that the number of trips is equal to an intercept, θ1, plus θ2 times the cost. And I have a theoretical argument here that says that t decreases when c increases. So it means that the θ2 parameter must be negative. Okay, so you see the idea. So I'm in a context where I have a true model on the one hand, and I have a theoretical model, which is the analogy of the discrete choice. And then I will generate data from the true model. I will analyze the data using my theoretical model on the one hand, And then I will analyze the data using machine learning data-driven model on the other hand, without theory. So this is the true data. So this has been generated using the true data generation process. So you have the cost as the x-axis and the number of trips as the y-axis. And here you see three curves. You have the true model here, what I call the theoretical model here, and here you have the data-driven model. So in this case, I have performed a regression of the two models on the data. So the first model is the theoretical one, which includes the fact that I believe that the number of trips will decrease with public transportation, while the data-driven model is just a general model that does not include any assumption. And actually, the data-driven model, because it has more degrees of freedom, will fit the data better inside the data. So it will be quite good for interpolation. But when you do extrapolation, what you observe is that, well, the true model, which is here as a reference, the theoretical model makes a mistake because you don't have the right specification. But the data-driven model also does a mistake. So both models are wrong. But the point I'm trying to make here is that the theoretical model is more useful because it captures the fact that the cost influences the number of trips in a negative way. If you use the data-driven model, if you increase the cost, you will increase the number of trips, which is inconsistent with what you expect, and therefore cannot be used for practical application. So the point is that thanks to theory, we expect the theoretical model to be a little bit more robust than data-driven models when you do extrapolation. There is a nice quotation by a chief economist at Google that says that naive empirism can only predict what has happened in the past. It is the theory, the underlying model, that allows us to extrapolate. And this is basically what I try to illustrate with this simple example. The next aspect that I would like to discuss is the so-called what-if analysis or policy analysis. It happens when you want to use the model to test decisions that you want to make and the impact of these decisions on the system. So you want to check the impact of new taxes or subsidies in a transportation system, impact of investments that improve the level of service, impact of some laws, restrictions, constraints, also some impact of modification of the choice set when you introduce new alternatives or you remove some alternatives. Discrete choice is actually designed to do that because it's based on a behavioral assumption. We capture the causal effect between X and I using behavioral theory, and we assume that this causality is stable over time. Therefore, we can manipulate X as we want, of course within the scope of validity of the model, and observe the consequences on the choices. We can change the choice set, we can include new alternatives, we can modify the value of X's, and so on. In the context of machine learning, this is designed to capture the correlation in the data, and as we saw before, basically the interpretation that we have for the machine learning model is that it somehow captured the ratio between the distribution of the full data, including the label, and the distribution of the features. So this is designed to be used when X is drawn from P of X. But if you modify P of X, it doesn't work. Somehow you would have to retrain the model. Okay, so the model has inside itself, it's hidden, implicit, the distribution of X, and a what-if analysis will modify this distribution, and the machine learning model will not be useful in this context. The next topic is about sampling, and I refer you to the lecture on sampling if you want to have a detailed discussion about sampling in the context of discrete choice. In the context of machine learning, somehow the data is the universe. The main argument that is used there is that the set of data is usually so large that it has to be representative of the underlying population. And most of the time in machine learning, the research question is posterior to the data collection, and it's particularly true for transportation context. In the context of discrete choice, we are doing inference and not data processing. So we follow a process which is standard in statistics. We identify a population, we have a research question, we design and implement a data collection strategies, and if there are sampling biases, we are aware of them and we can correct them. And again, this is discussed at length in the lecture on sampling, how to do this in the context of discrete choice. So what are the implications? Well, if you do classification, the main implication is that it biases the parameters. But in machine learning, you don't care about the value of the parameter, so it's not at all an issue. And if you are interested in interpolation, the machine learning approach is valid as we discussed before, so this is not an issue. If you are interested in extrapolation, well, this issue may be even amplified in this context. But the main problem comes in the context of aggregation again. And one typical example where the problem can be severe is counting. Because again, you have aggregation biases. And we have already discussed the issue about aggregation biases. It is relevant here as well. Well, one example came to my mind when I took a Uber to do a trip in the US, and I saw in the car that the driver had two phones. I said, why do you have two phones? I said, because I'm affiliated with Uber, but I'm also affiliated with Lyft. And depending on the most interesting proposals, I select one or the other. So it means that there are several people with two phones who are driving in the city. Now, take the point of view of the analyst who is collecting phone data, like the trace of all the phones in the city. This is big data, you can apply machine learning. But the data that you have is about phones. It's not about drivers. Okay, so you may have a severe sampling issue here. And if you want to count, so if you want to predict congestion, for example, to have information about congestion, the data about phones may not be appropriate. It doesn't matter which technique you use, discrete choice or machine learning or whatever you, well, the fact that the sample that you have is not representative does not allow you to derive counting data like flows or congestion from this data. And this has been illustrated by my colleagues. So using an example from the city of Geneva, data collected in 2017. So they had phone data, as I described, and they used the phone data to infer the flow on the street in Geneva. We also used a machine learning algorithm that was actually provided by the phone company. So the raw data, the output of the machine learning algorithm, and then they compare these output with the loop detectors that are available in the city that report the flows of cars directly measured from the cars. And this is the result. In this case, both the phone data and the machine learning algorithm were underestimating the loop detector data. So in this case, it's not because people had two phones, I don't know the reason, but clearly when you compare the two results, you see that there is a big mismatch here. And the reason is that there is a sampling issue. The last aspect that I would like to mention when we compare discrete choice and machine learning is interpretation. So machine learning methods are designed to predict. As I mentioned, they are designed in a way that they can reproduce an outsourced sample data as well as possible. But models are also used to derive quantitative indicators. In discrete choice, we use willingness to pay, social welfare, elasticities, and so on. But these indicators require a theory, a structure, that is not available in machine learning. And they are very useful to do what I call sanity check. So when you estimate a model, you have some willingness to pay, social welfare. Well, you can go to the literature and compare your results with the published results and interpret the differences. Also, the use of these indicators is very useful to communicate with practitioners. And it's a matter of trust. If you provide them with a black box, they may not like it. So the idea of opening the box, of showing what are concretely the assumptions behind the model, is extremely useful for the sake of the analyst, for the sake of the practitioners. So let's take some of these indicators. For example, elasticities. Well, elasticities can be calculated with machine learning models. What is an elasticity? Is the derivative of the model with respect to a variable, which is scaled by multiplying the value of the variable and dividing by the probability. Okay, so point elasticity can be calculated numerically. This is okay. Arc elasticity are more complicated. Basically, we are facing the same issue as what-if analysis, because to do arc elasticity, we have to manipulate the distribution of X. And this has been discussed in the context of the policy analysis. It may not work with machine learning models. For the other indicators like willingness to pay and social welfare, well, these concepts are based on utility theory, which is not embedded in machine learning model. So what researchers are starting to do now is to try to combine both. So to have a machine learning kernel that has all the advantages of machine learning, but to add a component from utility theory so that you can actually derive these quantitative indicators. And I refer you to a paper by Sifringer and co-authors for an example of this combination. So to summarize, I would like to compare discrete choice and machine learning based on various dimensions. So discrete choice are driven by theory, from economic theory, while machine learning methods are driven by data. Discrete choice captures causality, which is assumed by the theory and estimated by the regression model. Machine learning captures correlation. In the context of discrete choice, the focus is on interpretability of the results. In the context of machine learning, the focus is on the accuracy of the prediction. The model is different. In the discrete choice case, we call it a choice model, which is derived from the theory that we talked about. In the machine learning context, it's called a classifier. As we discussed, the model selection is based on different concepts. In discrete choice, we use statistical theory and hypothesis testing. In machine learning, it's more out-of-sample validation. And the main usage of discrete choice is to do what-if analysis and policy analysis, while the main usage of machine learning is to do interpolation. So this lecture was not actually a lecture. It was some thoughts that I had about this comparison of machine learning and discrete choice, because it's actually a very active field of research. A lot of people are really interested in combining the two. So you have several research trends, which I cite 3 of them here. First, you have the use of machine learning for choice data. There are plenty of papers in the literature. I just mentioned a couple of them here. Then there is a trend to try to combine the two and to get the best out of the two worlds. So using the machine learning strengths in discrete choice while keeping the context of discrete choice as we have discussed. And then there is another trend which is more about using machine learning to assist the specification of discrete choice models. And I refer you to this literature and other papers that are coming to get interested in this very interesting field of research. So choice data can be analyzed using machine learning methods. Some pitfalls must be avoided. We have discussed deterministic classification and panel data. It's easy to fix. We have also identified contexts where discrete choice models are potentially more appropriate than machine learning methods. Extrapolation, policy analysis, sampling, and interpretation. The best practice is to exploit the respective strengths of each approach and to combine them when appropriate. They are complementary. And as I said, this is an exciting field for research.